Hello, family. It's Kuseko again signing in. So we said Heat have the four videos first, and it have the three parts. The first video I talked about the thermometry. It ended. If you haven't looked on it, just go and search for it. The second video is about the heat transfer, and here we have the two videos. We have the convection and radiations, and we had about the conduction. So the fourth video will just be about the thermodynamics. So let's go on for the convection and the third videos, which is about the convection and radiation. So I'm going to talk about the convection and radiations here. So talking about here, what am I going to speak about? I'm going to speak about the convection, convection, the thermal convection, and what we say about the thermal radiation. Radiation. So I'm going just to speak about these two things here in this video. Okay. Take your exercise book and note everything that I'm just going to speak. So first thing that I'm going to talk about, I'm just going to talk about what we say the convection, the thermal convection, thermal convection. So talking about the thermal convection here, I'm just going to talk about the four things. One of the things I'm just going to discuss about what we say the demonstration. What is actually the thermal convection? Demonstration. I'm going to demonstrate. Demonstration. Told you, note them down before I just speak. The second thing is about what I'm going to speak about the types. After knowing what is thermal convection, now we are just going to discuss what are the types now. Types of thermal convection, and after that we are just going to discuss about the laws governing this thermal convection. There are two laws. The Newton's law of cooling and Peterson-Dulong law. We're just going to discuss about them there. Now upper is where you form sixes you need to focus much, because I'm just going to use them this week on solving the problems, the practical problems on theory. I'm going to use them to discuss about the theories of the practicals. You call them usually forging. Here chips. So focus on this one, those form sixes. And so I'm just going to discuss about the applications. So from 5, just pass on them. So let's talk about the demonstration of the thermal convection. What's actually the thermal convection? When I spoke about the thermal conduction, I just said it's the transfer heat from one point to another without the visible motion of particles. So there is no visible motion of particles in conduction. But here talking about the convection now, there is a visible motion of particles. So as the heat being transferred from one point to the other throughout the medium, there is a visible motion of particles of the medium. So that's what we say the thermal convection. So it's the transfer heat from one point to another with a visible motion of particles in a convectional current. Actually, here, let me demonstrate it here. So talking about the thermal convection, for example, here, now you have a centenary liquid here. You are heating the centenary liquid here, and we have a centenary wire goes here, and we have a triple stand here, and we have a source of heat here. Heat source. Heat. We have a source of heat, and here there are some liquids here inside. Some liquid is being heated. The liquid is being heated. Liquid being heated here in the beaker. This is the beaker. So this is the beaker, and here this is what we say the liquid. This is the liquid being heated. Let's say now at this level here. Now this is the liquid action. Now particles here below, just in contact with the wire goes here downward, tends to gain energy faster because they're in contact with heat than this one. So the particles here downward gains the heat, the kinetic energy, and they tend to be look here. When they gain heat, those particles tend to expand. Their volume tends to increase. And their volume increasing, meaning their density tends to increase, because talking about the density is the degree of compactness. So they become more lighter, and this just moves upward. As they move upward, these ones which are cold ones are heavier because they have just very small volume. So they tend to come down on because they are heavier. They come down on. So that alternative, as they come downward here, they get also being heat. They get also to be heated and then moves up again to depress. So these ones, hot ones depress the cold one. The cold ones depress the hot one. The hot ones depress the cold one. So that motion of the particles due to differences in densities is what we call, we say the convectional thermal convection, because now heat is being transmitted from downward to the upper molecules, continuously, so as the heat is being transferred throughout the liquid from the heat source, is what we say the thermal convection. Do you see now? Yeah. So actually the thermal convection is now, it can have the two types. The two types here, types now. Talking about the thermal convection, it has the two types. Types, chief, of thermal convection. One of the type is what we call the natural convection. Natural convection. And the second one is what you say the forced convection. So, talking about the natural convection, what about the natural convection, man? So, talking about the natural convection here, let me discuss about the natural convection. So, talking about the natural convection here, we are just discussing the type of convection which is caused by the differences in densities between the 2 points or the regions of the fluid. This convection actually occurs only for the fluids, not for the solids. For the solids, it's conduction. But here, because it's particles, the reason is why the particles, talking about the states of matter, the liquid, the solid, the gas, is actually the function of the intermolecular forces. So if your intermolecular forces have the very strong forces in between them, that's what we call the solids. If they have just weak, they are liquid. If they have very negligible strength, is what we call the gases. So actually, talking about in the solids, because they have the strong, you can't move the particles in the convection form easily. The heat conduction is easily conducted in solids in what we say conduction method. But in the fluids, the gases and the liquids, because the particles are the intermolecular forces, the intermolecular forces are just weak. Now that's what we say the convection. So the convection tends to occur in the fluids. Only occurs in the fluids. So it tends to occur in the fluids. So let's back then to the types of convection. The natural convection. Talking about the natural convection actually here, we just mean naturally. Okay, natural convection. The type of natural convection, we say this is just the convection of the transfer of heat from one point to the other due to the difference in density. So the criteria here is the difference in densities. Between the 2 points. So heat is being transferred from here downward to the upper side due to difference in density, because as they become heated, they become more lighter or the less denser, and so moves up, and the cold ones comes down to replace the other, and then the cycle continues as the whole liquid is being heated. That's what you say. So the best examples here, is just like boiling water in a beaker, like that. And the other example is like land breeze and sea breeze, land and sea breezes. We'll just look on them. The other example is like the refrigeration. Yes, we talk about this later. Heating of the loom, even the heaters, heating of the loom, heating rooms, even in the transformer cooling using the transformer oils. That's all the applications of the natural convection. The difference in densities is what causes the transfer of heat from one point to the other. Then that's about what we call the natural convection. Let's go to talk about what we say the other type, which is the forced convection. So we have just discussed about the natural convection and its examples. Let's talk about the forced convection. We just discussed it well in the applications here. In the applications, I'll just talk well about this. What's the forced convection now? Let's discuss about the forced convection. Let's discuss about the forced convection. What's about this forced convection? Talk about the forced convection, man. Forced convection is about what we say the movement of heat from one position to the other, but actually the movement of heat, the transfer of heat from one position to the other, but what causes here is the external force or the external blower. So there must be for example, if you have a hot food and you want to eat, what do? You just do you see? So when you apply an external force to cause the movement of heat from one point to the other, is what we say the forced convection. So the other type of convection is what we say the forced convection. Forced convection. Let's discuss about the forced convection now. Forced convection. So actually about the falsely convection. So about the falsely convection. This is by the what the criteria of classifying this. This is external force, or blower. Blower or a fan. A good example is like you are using a fan to cool your body, cooling the body by using a fan. You have your fan of fan example is cooling a body using a fan. Or for example, in the experiments, whatever from 6, you just go. This week I'll just teach about the experiments. I'll just tell you to make sure you cool your liquid by just stirring it. So you just force it to cool. You just say, for example, cooling by using a fan, cooling your food by blowing air on a hot food. That's forcedly convection. So you force your food to cool. That's what we say, the forced convection. That's another type. Let's talk about the laws, man. Let's talk about the laws. The third thing that I'm going to discuss with you is about the laws. If you don't have my books, make sure you download. You just go and DM me on WhatsApp and take the books for HIT. That's good books. They have a lot of solved questions and some criteria on how to do physics. Hey, gang, if you don't have my books, make sure you DM me on those numbers on WhatsApp and take you a book. There are my numbers down there. See you. And let's talk about the laws. Talk about the laws. We have the 2 laws actually governing the convection. So the convection, it doesn't occur just without the laws. Actually it occurs under some principles. So scientists sat down and did some experiments, and observers intend a real pattern that always operates in all forms of convection. And there are 2 laws. One of the law is what we call the Newton's law of cooling, and the third the second thing is about the Pettit and Durand law. Let's talk about the laws. 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 Let's talk about the laws of convection. Laws of convection. Laws of convection. Let's talk about the laws. Laws of convection. One is Newton's law of cooling. Newton's law of cooling. And the second thing is about what we say, the Pettit and Durand law. Pettit and the Durand law. So talk about the Newton's law of cooling. What does it state? So the Newton's law of cooling actually states this one is the modification of this one. I mean, the Pettit and Durand law is the modification of Newton's law of cooling, but they are the same law. But to some limitations, it doesn't work. Let's discuss about the Newton's law. You just see about it. So talking about the Newton's law, Newton's law of cooling. Cooling, it states, it states that the rate of cooling of the body is directly proportional to its excess temperature from the surrounding. If this object is 100 degrees centigrade and the environment is 25, so the excess temperature is the temperature that has exceeded from that of the environment. So that the excess temperature will just be 75. Do you get me? And so the rate of cooling of this object will just depend on how much it has exceeded from the environment temperature. That's what we say, the rate of cooling is directly proportional to its excess temperature to the surrounding. So if you have a hot object, it will cool faster than the cold object or than the normal temperature object. Why? Because it's a law. The rate of cooling is directly proportional to its excess temperature to the surrounding. So the rate of cooling, cooling is proportional, direct proportional, is directly proportional to the excessive temperature to the surrounding, that of the surrounding. So when talking about this, we say the rate of cooling is the heat lost per time is directly proportional to what we say, the temperature of the object minus the temperature of the surrounding. That's what Newton says, i.e. mathematical. But we say We can make the analysis of this. Hey, from 6 now, pay attention here, because this law is what we use in forging, in the theories of the experiments. So we make analysis, mathematical analysis of Newton's law, analysis of Newton's law. Hey, look here. Then look here, if you have a certain liquid here, the heat it can lose or absorb depends on its specific heat capacity. Heat will just be mc, the change of its temperature. So if we find the rate of losing here, we divide by time, but heat loss is this one. So actually, if this is the heat lost, it's just equal to rate of losing heat is just equal to mc, the change in temperature per time, per change in time. So if we have the change in heat lost, the change, the differential for is just equal now to what we say the rate of losing as per newtons. So here we put the constant K, but the excess temperature, theta minus that excess temperature, is from Newton's law of cooling. Do you see it? Yeah. So from there, I can now say some issues that I can combine the like terms to the like terms so as I may integrate the values. But you see, if I make K over MC, so if I say K over MC here, but times dt, but the like terms is temperature and temperature. Let me correct them, temperature and the change of the excess temperature here. What is this? If I integrate this value, keep in mind this, the rate of cooling. So the heat continues to increase as per time. So the heat continues to increase as per time. You see? So this K over MC, let me make another constant here, lambda. But you know in your mind, this lambda is the specific, is the thermoconductivity, the constant here from the Newton's law, and we have the mass and the specific heat capacity. So we say, talking about this lambda here, I just say d theta over what we say theta minus that of the surrounding is just equal to lambda but to dt, negative. Do you see? So when I integrate the time, when I integrate the temperature from a certain limit I've just been given, from where I will start to the where I will end, I just get now after that integration. Hey, if you haven't started about what we say the integration or differentiation, going to start them before coming here. So we just say, I'll just do it then here. Newton's law of cooling now. Rate of cooling. So what I just say here. Okay. So I can say here, if I integrate this, I just get ln of theta minus that of the surrounding. Then I get what is equal to negative lambda t. So what is going on here? But plus what we say the constant, because I have no limits on my integration. So what is this? Constant. You can just obtain the constant initially, as you know. So we just say at what we say time is just equal to 0. What is this now? If this is 0, then A will just be equal to this, but at the temperature which is now theta equal to 0. Meaning at this, meaning at theta is just equal to theta naught, meaning at 0 new centigrade. 0 new centigrade. So at this, the initial value, at times as soon as 0, the temperature is just the equal to initial value. Now A will just be A. If I put this equal to, so let me substitute the values. Actually, let me substitute the values. If I say ln of this initial was theta naught, that is for initial temperature minus the surrounding is just equal to what is this? Negative, but this is 0 T. Then I plus A. So if A, I can just get A is equal to what I say ln of theta 0 plus that of minus that of the surrounding, minus that of the surrounding here. So I can come and substitute this value here to get at time t at the theta, at the certain theta. So ln of a certain temperature and that of the surrounding actually is just equal to negative of what I say this times t, but what is A here is ln of theta naught minus what we say that of the surrounding. You see? So getting this actually here, this lambda per t is just equal, this comes here to be minus here. So Lm, and this is that of Q minus that of the surrounding, but minus what we say the ln of theta naught minus that of the surrounding. So actually talking about this ln, or just have talking about the F, theta minus that of the surrounding of that of the initial temperature minus that of the surrounding is just equal to negative what we say negative lambda t. So you can just slice, because it just follows the principle for logarithm. I just slice them now. Hey, whoo, sad. Oh yeah. So I just slice it here. So let me make it clear here. Let me make it clear here. I came to write it here. So I just slice that. I just say ln of what we say theta minus that of the surrounding chief over Q naught minus that of the surrounding, and then we have what we say. So this ln comes and lies here as L night of lambda t. Do you see? So getting the temperature theta for that time t, we just say is equal to this times this. This comes here to be plus the surrounding. So we plus what we say Q naught of that of the surrounding, the difference, the excess temperature initially, times E, but negative T minus T. So on forging, on your experiments here, you just use this principle. You just use this principle here. So you just determine first the excess temperature. The initial excess temperature is the one that you just use in your forging for a given time and for a given temperature. So you just be given, depending on the table, either the temperature or to find the time. So you find the time, or so you forge it to just save time in your experiments. That's all about the forging. I'll just discuss it with you this week on this experiments of for heat. Let's go direct to the applications, man. Let's talk about the applications for heat. Applications now. Let's talk about the applications. 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 Let's talk about the applications. Let's talk about the applications. So how about the applications? Actually, when I'm talking about the applications now, when I'm just speaking about the applications, there are more applications of convection in this life. But I talk about only four applications of convection here. So as I motivate you to go and start about, in my books, there are many applications there, so you go and read them. Let's talk about, very important is about the land breeze and sea breeze. What about the land breeze and sea breeze? Land breeze applications now, applications of what we say the convection. Oh, okay, let's talk about one is about land breeze and what we say the sea breeze. Hey, land breeze and sea breeze. Land breeze and sea breeze. Land breeze and sea breeze. So talking actually about the land breeze and sea breeze, look here. If you have, this is the land man, land chief, and here this is the sea. So the sea contains some water here, like this water. So actually during the day, chief, during the day, here we have a sun, sun like that, emitting some radiation toward the earth. So the land, since contains sand, it have sand. Sand is more conductive than water, because sand tends to contain some metals here. So since it contains sand, the land is more hot, more hot during the day. Do you see? Being hot and here being less hot than here. It's not that it's too cold. It's also receiving the radiations, but here receives more radiations than here. What happens here? Some lights are being reflected than being absorbed than here. So here, actually during the day now, when you are explaining about the land breeze and sea breeze, you just say for a land breeze now, which occurs during the day, land breeze. Land breeze tends to occur, we say the land breeze and sea breeze tends to occur during the day. The sea breeze. Upepo wa bahari tends to occur during the day. So what happens here? The land is more hot, so the air above it is more hot. So the air becomes hot. So if it becomes hot, the air here, as it's hot, rises because it becomes less denser. As it rises up, chief, during the day, this cold one, less hot, comes to replace this here air. Air above water is less hot. Less hot comes to replace this one. So air which has just rises, as this comes to replace this one, this air falls down. The cold one falls to replace this one. As falls to replace this one goes to replace this one. So the convectional movement of air is what causes what we say the sea breeze. So kuna upepo wa bahari this time. You see, during the day. But what we say the land breeze is here. Land tends to breeze toward the sea. What causes the flow of air toward the sea? It's because during the night, now, chief, the sun has just disappeared. The reverse occurs. Why? Because here becomes more cold. This becomes cold, chief. Air is now cold. So if it's cold, the direction is reversed. The direction is now reversed, chief. It's close to repress here. Here is more hot. It's no less more hot. So than here. So tends to reverse the direction. So the air tends to rise here. As it rises, the cold comes to repress. And so as it comes, this one also comes to repress because this one has just fallen down here. So the convectional movement of air is caused by the differences in intensities, is what we say the land breeze and sea breeze is caused by the natural convection. Natural convection due to heating, due to radiations from the sun actually during the day and during the night. So it occurs during the night, the sea breeze, the land breeze. That's what we say about the sea breeze and the land breeze. I think you have just got me about that. So let's talk about the second thing. The second thing actually is about the second application is about refrigeration. Refrigeration. You see? How about the refrigeration? Talking about actually the refrigeration, this is how the refrigerator works. So in the refrigerator, what happens here is that heat from the cooling system is just being pressed on the upper part of the refrigerator here. If this is the refrigerator, this is the refrigerator. So here the cooling unit is just pressed up. Why the cooling unit is being pressed up? Because when pressed here, air molecules should just be cooled here and become more denser. So here, making the air become denser. So they fall down. The lighter one are now moving up to replace that which has just fallen down, which are more denser. So that more movement, when the lighter comes here to the cooling units, they also being cooled and then comes down. So what happens here is like there is a convectional movement of air. But what happens if you press the cooling unit downward? When you press it downward, what happens here is that you can't cool the foods upward because you just cool downward here. So there is no source of convectional current because the denser molecules just remain downward and the hotter one will just remain hot. That's why we put the cooling unit upward. One of the best questions you asked me, Mr. Kuseko wants to cool his room. I asked them in 2022 in my examination series that I'm just going to start them on January for Form 6. I asked them in 2022, I asked them that, how, Mr. Kusekwa, I just paraphrased the question, I don't remember it exactly, but you just go and look to my series. I said Mr. Kuseko wants to cool his room, and so he has taken his refrigerator and pressed it under his bed so as to cool his room. Explain to Mr. Kuseko as the best students of physics that what he's doing is an intellectual or physical masturbation. It doesn't work in real world. Can you explain to that now? Yes, you can. So you say the room won't be cooled because the air just below, just under his room will just be cooled, but won't get the chance to move up because the air density will just remain downward. So the air up will just remain hot. So he won't succeed to cool his room. You get me now? Yeah, that's why. That's how we do, Chief. And how about the that's about the refrigerator. So the cooling unit is always pressed upward so as to initiate that convectional current. The third thing is about the heating of the system. Heating systems. Heating rooms. Heating rooms. Let's say you want to heat your room. What do you do when heating your room? You just press the heating system downward. Why? So as to make those molecules downward to be lighter, and so they just move upward so as to go and the cold ones to come downward so as to get heated and to cause the convectional current repeatedly. So what happens here? We put the cooling systems up, the heating systems downward. Why? To cause the convectional current, actually, by causing the heating system, by causing the colder and denser molecules to be lighter and move up, and the colder ones to fall down due to their density so that they may get cooled, and the convectional current continues so as to heat the whole room. Here about the heating system. How about the fourth thing that I'm just going to say is about, let's say, about the transformer cooling. Transformer, very important, cooling. Actually, in transformer here we use the transformer oils. Hey, when I was just speaking about the electromagnetism, if you haven't looked to my video on electromagnetism, just go back and study about it. So when we were in electromagnetism, I just remind you, just a reminder, I said in electromagnetism, the causes for heat in transformer, the iron losses. Do you remember? I said about the iron losses. Do you remember, Chief? Yeah, I said about the the copper losses. Do you remember? Yeah, I talked about the other loss is about the hysteresis loss. Very important loss. You need to know about it. If you studied the electromagnetism and you don't know about the causes for transformer, go and look to my video, Chief. And that's why you call me a father. Everything that you need to know about physics is here. I'm here. So just pray for me that I may not die early. Okay, let's talk about the transformer. Talking about the transformer here, transformer cooling, we just use the transformer oils. So if this is the transformer here, come and see here. This is the transformer is working here. We just press it in the transformer oils. This is the transformer oils. Why do we press in transformer oils? Transformer is always pressed. This is the transformer. So this is the cover. So transformer is pressed here. What's the reason here? It's just the particles here below. The particles here below just when the transformer is working, it loses heat, and this heat is being absorbed by the oils, and these oils, when they absorb heat, they are just turning them into the kinetic energy. They expand, so they become less denser, and they just moves upward to the upper layer. While these upper layers falls down due to their densities, they also gain the kinetic energies and become lighter and just moves up. While they move up, also they lose the energies in terms of potential energy as they move, and so they just come down. So they cool up the transformer oil. So the mechanism of cooling up the transformer is due to convection of the transformer oils. That's all about the convection. Done. Dang. So I said we discuss about the convection. What's the time there? What's the time? Let me look at my time if it's good. It's about 34 minutes. It's good. So let's go for radiations as fast as possible. Let's go for radiations. Let's go for thermal radiations as fast as possible. Thermal radiations. Let's talk about the thermal radiations. Thermal radiations. Woo! Physics is sweet enough. Yeah, I feel dang. Let's go on. So about the thermal radiation. Thermal radiation. Thermal radiation. Radiation. Let's talk about the thermal radiation here. What about the thermal radiation? Talk about the thermal radiation is also the method of transfer of heat from one position to the other, but actually without heating of the intervening medium, chief. You get me? In conduction, I said when heat is being transferred from one position to the other, there is no visible motion of particles through the medium, but there is, because we studied about the mechanism and we know there is a vibration of particles in about the middle position, and there is a motion of electrons. So there is a vision, there is the involvement of the medium here. So the medium particles are just in motion. But talking about the convection, we said there is a physical visible motion of particles in convection occurrence. But now when we are talking about the thermal radiation, there is no involvement of the medium, and there is no either visible or invisible motion of the particles of the medium. So what is happening here is just the transfer of heat from one position to the other magically. No, don't say that in physics, it's not magical. But what you say, without hitting the intervening medium. So there is no involvement there is no heating of the medium throughout as heat is being transferred. What happens here actually, look to this. What happens here is because heat is being transferred in terms of radiations. Radiations, what we call which contains the radiant energy. Come on. So talking about the radiant energy, for those PGMs and those who don't start chemistry, just studies physics, there is a topic called the general chemist, or students for chemistry always studies about what we call the radiations. So actually, radiations, the radiant energy has the three parts for your advantage. It had three parts. So talking about the thermal radiation, let me discuss about the thermal radiations first. The objectives that I'm just going to discuss here about the thermal radiation, I'm just going to talk about the radiant energy. Radiant, very important. Radiant energy. Let me talk about the objectives here. Objectives. And so I'm just going to talk about the radiant energy. The second thing that I'm just going to talk about things like just about the black body. Do you know black body? I'm just going to talk about things like the black body laws and the black body, how to realize the black body, the energy distribution for the black body. So I'm just going to talk about what we say, the Kirchhoff's and the Prevost theory. Kirchhoff's and Prevost theory. And the fourth thing that I'm going to talk about it, Chief, is the estimation of the Earth and the Sun's temperature. Estimation of Earth and Sun's temperature. Hey, let's discuss about these things, man. Let's talk about the radiant energy. What's the radiant energy, man? Yes, my camera is okay. Hey, let's talk about the radiant energy. So talking about the radiant energy, this is now the energy that is being transferred in electromagnetic form from one position to the other as heat. And when we talk about the radiant energy, is actually the electromagnetic spectrum, and we say radiant energy is made of the three components. One is what we call the infrared. The second thing is about the visible region. And the third thing is about the ultraviolet radiations. Visible radiations. We have the infrared radiations. So actually heat being transferred in form of radiations without hitting the intervening medium, that's what we call the thermal radiation. So look here, Chief. Heat is actually here in this zone. Here, what the properties here? We have very large wavelengths, less energetic, there is no much energy, and we have the less or smaller frequencies. So we have these things here about the frequency, energy, and wavelength. Look here, to those who don't know about the spectrum, electromagnetic spectrum. This is about the electromagnetic spectrum. Here, radiations. Hey, Chief, look here. Here is where we say the colors are visible. The red, orange, green, and we say low GBV. Blue, indigo, violet. This low GBV. Do you see? So we say this. When we say the infrared, this means they are refracted less than lead. Refracted less than lead. But talking about violet, refracted more than violent. That's why we say ultraviolet. But less, we say infrared, less than red, refracted less than red. So heat is here. That's why we say heat is infrared. Heat radiations are infrared. So every object in the world tends to radiate the radiations and absorb the radiations. So even if its temperature is just maintained constant, previous theory tends to say it's just absorbing and radiating in the same rate. So what we say, if the heat is in radiation form, heat are what we call the infrared, Chief, infrared. Do you see now? Yes. So from there, let's talk about now the black body. You have just understood about the radiant energy now. So actual heat is being transferred as infrared here in this zone only, not colored, not ultraviolet. Let me talk about what we say the black body. What's the black body, Chief? What's the black body? And not the black, not the black body, not the black body. It's not black body, black body. For example, this mine is white body. Not that, Chief, not that. I didn't talk about that, Chief. No. I'm just talking about the black body, a body which is black. Black body. Okay. We say a blackboard is the body that tends to absorb all radiations falling on it. Hey, come on. If this is the lamp illuminating light to me, you see here, hey, if this is the object, when the light falls on this object, radiations, all radiations when absorbed, they can be reflected, they can be absorbed, just being taken by the particles, absorbed, and they can be transmitted throughout. So when radiations falls on the objects, there are three things observed here. 1 is absorbed, 2 is reflected, and 3 is transmitted. So talking about the blackboard, has no transmission, has no reflection, but it absorbs all of radiations falling on it. That's what we say the blackboard. So the blackboard, the best absorber is the best radiator. Take that note, big. So the best, good, we say the good absorber is the good radiator, Chief. But not the reflector. Don't mix. It's not the reflector. So if you are reflecting the light, this means you lose some light. It's not the good reflector. The absorber is the good radiator of light. Okay. So the blackboard here, I'm just going to talk now about the blackboard. You know now, the radiations that are being emitted by the black body is what we call the black body radiations. Black body radiations. These are just radiations being radiated by the black body. And so, talking about the radiation now of a black body, I'm just going to talk about it. I've just talked about the definitions, the black body radiations, and we are just going to discuss about these two things here. We're just going to discuss about the laws. we're just going to discuss about the energy distribution, and we're just going to talk about how to realize the blackboard. So on blackboard here, we're just going to discuss about how to realize a blackboard. A blackboard. The second thing that we're just going to discuss here, we're just going to discuss about the black body laws. There are 2 laws governing the thermal radiations of the blackboard. And the thing that is very important is about the how is it radiating, the energy distribution. By the blackboard. So we're just going to discuss about those things on a blackboard. Let's go on. So the black body of just understood is just the object which absorbs all radiation firing on it. So we just say it's how can you realize it? How can you realize that this is the black body? Hey, when you for example take a centenary tin object, you put it like this and you pinch a small hole through a blackboard and you allow a light from a far distance to fall through that hole. Then you observe inside, you see the blackness. That's the black body. Why? Because the radiations are just entered in, and then through multiple refractions here, at every refraction is being absorbed by the walls of that lid, finally the image has totally been absorbed, and that's why you see the blackness inside. So how do you realize the blackboard? It's just by pinching a small hole through a lid of the material, and the color observed inside will be black. Why? What's the reason? The radiations falling through a small hole pinched is always absorbed through multiple reflections inside. That's why the object, the real is just seen inside as black. That's how we realize the blackboard, by just pinching the small hole. But what are the laws now governing the black body? Laws of the black body radiations. Laws of black body radiations. Laws of black body radiations, chief. Here are the laws. The first law of black body radiations is what we say the Wiener's displacement. The Wiener's displacement law. And the second thing is about what we say is about what we say the about the Stefan's law. Stefan's law. Come on, chief. So when we are talking about the displacement law, Wiener's displacement law, we just say it states, the Wiener's displacement law, it states displacement. We say as you increase the temperature of the body, the wavelength at which the maximum energy is being radiated decreases. Remind you, chief, the hot object radiates more energy, so its temperature is very high. So as it is high, the energy radiated is being high, so its frequency should be large, and so its wavelength should be small, very small. So talking about that, that's why we say at maximum, the absolute, at maximum temperature, the high temperature, the smaller the wavelength. That's what Wiener speaks. So we just say the absolute temperature at which the body radiates heat is inversely proportional to the wavelength at which the maximum energy is being radiated. So it states the wavelength at which the maximum energy is being radiated is inversely proportional to its absolute temperature. That's all about. So we say the wavelength at which maximum energy being radiated is inversely related to its absolute temperature. You see? Yeah, that's all about. So removing this maximum here, removing this, yeah, 1 over t. Removing this, we put the k, which is what we say the Wien's displacement constant. Let me put b. B is the Wien's displacement constant. You find it in your calculator, 2 point something, 0.9 something. How about this Stephen's law? Let's discuss about the Stephen's law now. Talking about the Stephen's law, we are just saying about, we are just talking about Stephen's law now. Talking about the Stephen's law, we are saying, it states, actually the power radiated, the energy radiated per time per given area is direct proportion to the fourth power, which is absolute temperature. That's how it states. So energy radiated per time is what we say the power radiated by the object per given area. Is just direct proportion to its absolute fourth power of absolute temperature. And so when talking about the power, this is just equal to area, but when you remove the constant here, constant K is just equal to Boltzmann, is what we say the Stephen's constant here. So Stephen's constant by the temperature power 4. Do you see? That's about what we say the Stephen's law. Those are laws governing the black body radiations. Hey, these laws now can be distributed. The energy radiated by the body is not randomly. It's not randomly radiated. They are radiated depending on these two laws. The Wien's displacement law and about the Stephen's law, the power radiated per given area. So there are laws here. Laws here is what we say the power is equal to Boltzmann's constant T exponent 4. This is all about. So there is energy distribution curve that you need to know. Actually, it's not randomly radiated. It obeys the law. So if this is the energy radiated by the black body, the energy, this is about the energy. And this is about the wavelength of radiations radiated by the body here. So when the area under the curve, so there are things that you need to know here. Area under the curve represents the energy radiated. So see here. So when chief, for example, this is the body here. This is the body here. Let's say this is the body here. This is the body. You see? So if this is the maximum energy radiated by the body, the maximum energy at the temperature, let's say of 100 Kelvin. So this is the wavelength at which the maximum is being radiated here for 100. So the area of this curve, chief, this area represents the energy radiated by the black body. You see? The second thing here to note, as you increase the temperature, the second thing, the temperature, as the temperature increases, is directly proportional to what we say is inversely related to the maximum wavelength. The maximum wavelength increases. So the temperature at which the maximum energy is being radiated increases with the temperature. So, for example, if I put the object, if I increase the temperature of this object to 200 here, I expect its maximum wavelength, where the maximum energy, here is the maximum at 200 here. Do you see where the maximum is being emitted? Its wavelength tends to decrease. So the wavelength tends to turn back here toward 0. Do you see? As the temperature increases, now the temperature here, chief, is about 200 K. Even if you increase more, when you just increase more, the more it just increase. So here it's just let's say about now K. Do you see? The wavelength also tends to increase more, to decrease more, to decrease more. and the maximum wavelengths at which it's radiates. The same chief when you just increase, yay. So tends like there is a locus here, and the locus here we put to observe that. So it just tends to the wavelengths tend to increase as you increase the temperature here. As you increase the temperature, do you see? That's the second thing to observe. The third thing is about the power. But the power radiated, the energy radiated here increases. The energy radiated per time, the energy radiated per time tends to increase. Do you see it was here? It's here as the temperature increases from 100, 200, 300, 400. So as you increase the temperature, also the energy increases. So the energy is that proportional to their absolute temperatures. And it's what we say power 4. The Stephans. Do you remember the Stephans? Yes. This is the displacement observed here. But most of the parameters, the most good absorber, black bodies black in color are good absorber of heat. This is what observed here. Practically, the good radiator and the good absorber are the black bodies. That's how we speak about the black bodies. Let's go for the third thing. It's about the Kirchhoff's law and Prevost theory. Kirchhoff's law and Prevost theory. Kirchhoff's law and Prevost theory. So talking about the Prevost theory. What's the Prevost theory talking about? Prevost theory is discussing about what we say the thermal equilibrium. Hey, do you know the concept about thermal equilibrium? Have you ever heard about the thermal equilibrium? Okay, so talking actually about the thermal equilibrium. If you haven't heard about it, I'm just going for the third thing. Third thing here is about what we say the Kirchhoff's law and what we say the Prevost theory. What's about the Kirchhoff's theory here? What am I going to speak here? I'm just going to talk about the Kirchhoff's law and what we say the Prevost theory. So I'm going to talk about the Prevost theory first. Prevost theory. This describes about the thermal equilibrium. What about the thermal equilibrium? As you studied the chemical equilibrium, it's the same as the thermal equilibrium. So the rate, but here we're just dealing with absorption and radiation. So if the rate of absorption is the same as that rate of radiation, is what we say the thermal equilibrium. So actually talking about the thermal equilibrium is the condition or the states where now, chief, we say the rate of absorption is just equal to rate of radiation. Do you see? When they are just equal, is what we say the state is the thermal equilibrium. So the previous theory described that the objects tends to radiate heat. Condition for radiation of the heat conditions actually depends on, first thing is about the nature of the object, nature of the surface. The object radiates temperature depending on its nature of the surface, or absorbs depending on its nature of the surface. If you haven't followed me on Instagram, make sure you follow me on Instagram. I just demonstrated this video on Instagram. There is a person just illuminating, just using the lenses to focus the sunlight to the bottles, and so the bottles tends to burst. Do you see? Yes, but when we press the white colored bottle, it didn't burst. Why? The reason why it was not absorbing any kind of color, but all colors was just absorbing their own, just reflecting their own colors, but absorbing all the colors. That's why they were just bursting. But talking about the white color, it didn't. Why? It's because it's not absorbing. Go and look to that. So if you haven't followed me on Instagram, just follow me and then go and look about that. Let's talk about the nature of the surfaces. So talking about the nature of the surface, we're talking about the colors now. The colors Chief. The second thing that we are just discussing here about the conditions, about the nature, about the condition. The other condition is about the temperature, its own temperature, temperature of surface, temperature of the surface. So if the surface temperature is too hot, the body will just radiate heat. But if it's cold, this means it absorbs heat from the surrounding. So it just depends on its temperature and the temperature of the surrounding. Here, the temperature of the surface or that of the surrounding. Yeah? Temperature of the surrounding. So those are the conditions for the radiations. Yeah? The body can radiate if it's more hot than its surrounding, and it can absorb if it's more cold than its surrounding. And the fourth thing is about what we say. It's about what we say. Yes, we say the temperature. Yes, the temperature and the nature of the surrounding. Yeah? That's all about. So, what does the Stefan's theory state? Stefan's actually says, Stefan's actually says, it states, the body tends to absorb or radiate heat depending on its nature and the temperature, and its nature and its temperature, and that temperature of the surrounding. But when the object has just the constant temperature, this means it absorbs heat and radiates heat at the same rates. That's how the previous theory states. So the previous theory states, the body tends to absorb heat, and depending on its surface temperature and temperature of what we say the surroundings. But Chief, when body temperature is constant, this means the rate of absorption and radiation are equal in rates, are of the same rates. You see, that's how we say about the previous theory. Let's discuss about the Kirchhoff's law. Let's go direct to the Kirchhoff's theory. Kirchhoff's theory. Let's talk about the Kirchhoff's theory. Let's discuss about the Kirchhoff's theory. Hey, talk about the Kirchhoff's theory. Hey, my marker pens na over. Kirchhoff's. Kirchhoff's law. Kirchhoff's law. So talking actually about the Kirchhoff's law, what does it say? Kirchhoff's law is say that go to my books. If you don't have my book, make sure you DM those numbers on WhatsApp and get your book. It's just free. Everything is free. But after sometimes I'll just start to sell them. So you make sure you hurry up to get the books. Very good. So actually speaking about the Kirchhoff's law now, Chief. Kirchhoff's law, it explains about the absorption and emission of the radiations. And so, talking about the Kirchhoff's law, it says, at a given wavelength, specific wavelength, the absorptive power over emissive power, this is constant and is equal to the emissive power of the black body. So it states at a given wavelength, the ratio of emissive power over absorptive power is just equal to emissive power of black body. And it is constant, Chief, for that wavelength. So but not here. For a given wavelength, if you change the wavelength, that ratio also changes. So that's what we say the Kirchhoff's law of radiations. Let's now estimate the temperature of the Earth. surface temperature of the earth and surface temperature of the sun using the concepts on radiations. One of my students asked me, hey teacher, how could they measure the temperature of the sun and they say the temperature of the sun is this, or the temperature of the core of the earth? How could they do that? I told him politely, hey, she was a girl. I told her we can use the relativity concept or we can use what we call the pyrometer. I think when she comes back, she's now at school. When she comes back, I think she'll see this video and she'll enjoy it. If you see it, make sure you call me out. I saw you, sir. And so let's go on, man. Let's talk about now the estimation of the temperature of the sun. Hello, family. My master classes for September are just going to start for practicals, Form 6. Don't let me down. Come at Perfect Vision Ubungo, Dar es Salaam. No other way. No any other place to learn about forging. That's the exact place, man. So let's distort the concepts about the practicals. Let's distort the theories about the practicals. Let you know how to do the practicals as fast as possible. I asked my students and just researched it, or I interviewed them. Why couldn't you get some A's? I came to realize that practicals the problem, because every student could say, I just got the B, it's because practicals I didn't forge well in the current, time just erupts me in a heat, and whatever reason you say is valid. It's valid, chief, but it is not going to give you the results that you want. I just repeat this statement. Whatever reason, whatever excuse you give of not getting an A, it's valid. Chochote kile ile sababu yoyote ya kutopata hii utakayoisema ina mashiko, lakini haiwezi kukupatia matokeo unayoyataka. Never. Let's meet at Perfect Vision. I want to do something for you. I just visioned your A. I saw them, but if you can either decide to get them or you don't want. So let's meet at Perfect Vision. I want to give you some A's about practicals. Practicals was solved the problem on the last year, but I don't want that problem to occur again in 2025. I want your A's, man. Chief, let's move on about this. So let's talk about the estimation of the temperature of the earth. Estimation of temperature of earth and sun. So that's what we're just going to do here. So we have to estimate the temperature of the earth. Let me start with the temperature of sun here. A. What's the time? Let me estimate the time here. Okay, still ikifika na nusu, it's over. Let's go for this temperature of the sun. So before doing for this temperature of the sun, there are some assumptions that we always make. 5 assumptions that we always make in doing this, in calculating the temperature of the earth and the sun. Look here, get me clearly. You can just be given a calculation, and finally they ask you, and they give you 2 marks to explain. What are the assumptions have you made on measuring that temperature of the sun? So you make sure you know about the assumptions we are doing here. First thing, we are assuming that the earth and the sun are the perfectly black bodies. But you know water tends to reflect light. And so we contain seas on the earth. So does they not reflect the sun's radiations? They reflect. So the earth is not a perfect black body, but we assume it's a perfect black body. So one of the assumptions here made, assumptions, chief. Assumptions. 1, we say earth and sun are perfectly black bodies. The second thing here, chief, we just say the earth and the sun, the radiuses are very similar. The earth and the sun, the radiuses are very smaller. Radius of the sun and radius of the earth are very smaller compared. Radius of the sun and radius of the earth are very small compared to their distance apart here. Do you see? So the radius of the earth and radius of the sun are very small compared to their distance apart. Okay, the third thing here is about what we say. We say that the earth doesn't have any generation of heat from the interior. Why do we know? During its rotation, there is a convection current inside which gives the rise of temperature. Actually, we assume that there is no generation of heat from inside. So, no heat generation from inside. No heat generation started from interior of earth. You see, the fourth thing, number 4, actually we assume that there is no loss of heat as heat is being transferred from the sun to the head. So there is no loss of heat from the sun to earth shift. The fifth thing, number 5, we say, actually, Chief, what's the microphone? Yeah, microphone is okay. There is no any source of radiations from the except from the sun. So we assume the stars and other galaxies, they don't radiate their radiations toward the sun, the earth. So the only source of radiations, the source of which is only the sun. It's not other. So the earth receives radiations only from the sun. So earth receives heat only from the sun, no any other source. So there are 5 assumptions in doing these calculations, and so after understanding those assumptions is now we are just going to calculate about the temperature of the sun. Okay, so actually before calculating this, you need to know about the 2 terms which are very important. One is about the solar constant, and the second one is about the solar luminosity. So we need to know about the solar constant, and you need to know about the solar luminosity. So knowing about these 2 terms actually is what helps you now to calculate about the temperature of the earth and the temperature of the sun, surface temperatures. So what's the solar constant? The solar constant, its symbol is S, and the solar luminosity is LS. Look here. What is solar constant here? If this is the sun, do you see, before defining everything, you need to know. Defining means you express what is it. So you need to understand what is the solar constant. If this is the sun now, Chief, and this is the earth, do you see now? So if this is the earth here, actually talking about the solar constant, is that radiations from the, let me draw it in a larger size. So this is the sun, and actually this is the earth. Earth. So, you see, if this is the earth, the area of the earth which is perpendicular to the radiations from the sun receives a certain radiations, which is not as that all radiations falling on the earth. So, talking about the solar constant is the energy of the sun received by the area which is perpendicular to the radiations from the sun. So, talking about the solar constant is the power rate of receiving the radiations from the sun by the area which is perpendicular to the radiations from the sun. And so talking about the radiations, talking about the solar constant is the energy received per given time for a given area which is of the earth which is perpendicular to the radiations from the sun. So talking about the solar constant is actually the energy received per time. But talking about the solar luminosity. Solar luminosity, look here, Chief. Luminosity. This is the sun. The sun tends to radiate radiations to all directions, all directions, all directions. So if this is the orbit of the Earth, let's say Earth. Now, talking now about the solar luminosity. Solar luminosity. If this is the distance from the sun to the Earth, Allah. The distance from the center of the sun to the center of the Earth, Allah. Do you see? If R is the distance, this shows solar luminosity now is the energy radiated by the sun to all directions. So on calculating it, we say is 4 pi r squared, because it's a sphere. So the area that is being radiated is being illuminated by the sun as it radiates radiations is 4 pi r squared. Do you see? Then times the solar constant. And that area is the distance from the sun to that planet. So talking about the solar luminosity on the Earth is now that distance from the Earth to the sun. So the area times that solar constant is what we say the solar luminosity. So the solar luminosity is the power radiated by the sun to all directions. But this is the power received by a black body or the surface which is perpendicular to the radiations on the Earth. The radiations, the power received from the sun on the Earth by the area which is perpendicular to the radiations. That's what we say the solar constant, and this we saw solar luminosity. I've just explained it much in my book, so just find them out in my book. That's about the temperature of the sun. Let's talk about the temperature now of the sun now. Let's discuss about the temperature of the sun. So if I'm going to discuss about the temperature of the sun now, let me do it here. Temperature of the sun. Temperature, you have understood about the solar luminosity and the solar constant now. Let's discuss about what we say the temperature of the sun. Hi, temperature of the sun, temperature of the sun. How do we get it? Temperature of the sun, we just get it by comparison. We know the luminosity now is the power radiated by the sun. Luminosity, solar luminosity. LS is just equal to 4 pi r square and who? Solar constant. But we know actually that the power radiated by the sun as the blackboard from Stefan's law. Yes, says as it is the blackboard, the power radiated by the blackboard is in proportion to the fourth power of its temperature. So we said this is power radiated by the sun is the same as luminosity, because the luminosity is the power radiated by the sun to all direction. And the Stefan says the power radiated by the black body now, Chief, will just be the area times the radius of the sun, because this one is the blackboard. And so we say 4 pi, but the radius of the sun square, Boltzmann constant, and who? And we say the fourth temperature of the sun, exponent 4. Because Stefan says always, he says power radiated by the blackboard is just equal to times area times exponent 4. So the area is about this of the sun. So luminosity is just equal to power radiated by the sun from the Stefan's law. So we can say the 4 pi, but radius, this is luminosity. So R is now the radius from here to that planet, the luminosity. The square, but the constant, the solar constant, is just equal to 4 pi, radius of the sun square, Boltzmann constant, temperature of the sun, exponent 4. And so pi, 4 pi dies. And so we just have the radius. So temperature 1, the temperature of the sun now is the radius over the radius of the sun, and we divide by who? So this is Boltzmann and this is solar constant. And here, since they have the square, we cancel by 4, we just have the 2, but we have S over who? Over the Boltzmann constant here, but times who? Exponent 4. And so we just have the temperature of the sun. So getting actually the temperature of the sun, we are just going to get it as temperature of the sun. So the temperature of the sun as seen there, the temperature of the sun, you are just going to get it. Temperature of the sun is just going to get R over radius of the sun, a half, then who S over Boltzmann when divided here, but exponent 4. That's all about what we say the temperature of the sun. Do you get me? That's how you get the temperature of the sun, Chief. Let's discuss about temperature of the earth. Temperature of the earth now. Temperature of the earth. Let's discuss about the temperature of the earth. Temperature of the earth. Temperature of the earth. Temperature of the earth. And you need to know about the signification. So this is the radius between the earth and sun. This is the radius of the sun. This is the solar constant, and this is the Boltzmann constant. If these are just given there at the constants before starting your examination, are there. So Chief, and actually the Boltzmann constant is in your calculators. You just go and do it. And what we say about the temperature of the earth. So how do we estimate the temperature of the earth actually? So actually talking about the temperature of the earth, we approximate it by just relativity as normal. What do we say now? We say actually, hey, this board, okay, why is it shrinking? Okay. Okay, so talking about this, we know power. There is no external, do you remember the assumptions? There is no external generation of heat except that is coming from the radiation from the except that energy coming from the radiations of the sun. So power received by earth is just equal to power received radiated now. Because I say the good absorber is the good radiator. So power radiated, and we say this is the perfect black body. We are radiated by earth. So what is the power received by the earth? Power received by the earth, just to remind you, this is the earth now. Earth has just received from the sun. Do you see radiations here? So when I speak about the radiations of the sun as the black body, the sun tends to radiate a certain image, which actually is power radiated by the sun. It's just equal to the area of the sun, which is 4 pi, but radius of the sun square, then Boltzmann constant and the temperature exponent 4, but of the sun, according to Stefan's law, because it's the black body. And that radiated by the earth, according to Stefan's, is about the 4 pi radius of the earth square. You know that, Chief, you know about that. So Boltzmann constant T4, but temperature of what? Of the earth, because they are black bodies. But what remind you, but what you need to know, it's not the whole power of the sun that the earth absorbs. Dang. But only a fraction of this area, which is the area which is perpendicular to the radiations. So the power received by the earth, power of the sun received by earth, is actually equal to the area of the earth which is perpendicular, not the area of the earth, the area of the earth which is perpendicular, over the 4 pi r, but r is the total area now, because the luminosity is throughout. Do you see? Then times the power that has been radiated by the body, so as to get the fraction that has just fallen on the earth. So the power radiated by the sun, which is now, the power radiated by the sun is 4 pi, radius of the sun is square, Boltzmann constant, temperature of the sun, exponent 4. Do you get me? Yep, I get you. So talking about the power received by the earth actually, is this one. So the power radiated by the earth is this one, Chief, because it's the black body. Power now, power radiated by a black earth, by the earth. by what we say Earth is equal to 4 pi r about the radius of the S square, Boltzmann constant times the temperature of the S, exponent 4. Do you see? So when we compare this power received and power radiated, because they are equal, no heat loss or any other source, so we just say P pi radius of the S square, we have the 4 pi radius square times who 4 pi radius of the sun square, Boltzmann constant, that's the sun. 4 is just equal to what we say 4 pi radius of the earth square, Boltzmann constant, and we have the temperature of the earth, but exponent 4 here. So talking about that, chief, 4 pi cancels with the 4 pi. Is that good now? Yes. Pi cancels with the pi. Yes now. Boltzmann cancels with Boltzmann. Yes now. That's good. So talking actually about this now, what remains here, radius of the S over that radius A. But radius of the S cancels with the radius of the S chief square. So here we have the radius of the sun over R. And here we have the temperature of the sun and we have the temperature of the earth. But we have also 4. So 4 just remained here. And so, finalizing this, we can say now, temperature now, the temperature of the sun, but times what? The radius, which is now the radius of what? Of the sun. Over what? Over radius R. But over who? Over 4. So over 4, when with the fourth root is what we say here remains 2, while here remains T of the sun, because it is exponent 4. So cancels the exponent 4. So this is what we say the temperature of the earth. Temperature of earth. So getting the temperature of earth, man, is fucking dude here. Do you see me? Yes, that's good. Hey, chief. God bless physics. God bless my dance. May God give you an A. Go and study fucking hard. Don't just listen to my videos and then you go and chill down. Not only you won't get an A. Physics is a skill, so just go and fight. God bless physics. God bless the students. And let's say amen. Chief, see you signing out. It's your boy here.